So today we're talking about polar coordinates. And we begin by looking at an interesting graph in our calculator. We went to mode. And put our calculator in polar mode. Then we went to y equals. We entered this interesting graph. I'm going to show the equation for that in a minute. If we just press graph right now, it'll start graphing it. And this is something, there is no way we could have done this using regular coordinates, right? It's graphing like a butterfly. Okay, make sure that you're in radian mode. If you're not getting this, maybe you are not in radian mode. I'm going to show you guys the equation again. Yes, let me bring it back up. So again, the reason I'm showing you this is because I'm trying to show you polar coordinates are really, really neat. And you can do things with it that there's no way you could have done with regular coordinates. The same thing goes with parametric. Again, we talked about the usage in creating fonts for printers in parametric. Again, you can do really cool stuff with polar equations. And let me show that equation of that again in case you want to graph it yourself. This was the equation. So r equals e to the cosine theta minus 2 cosine 4 theta. Make sure this is in parentheses. And then sine to the third theta over 4. And the way we entered this last one was we entered sine of theta over 4, everything to the third power. That's how we entered the calculator. And these are our parameters for theta, x, and y. And one thing I pointed out to you was the key that shows you like x theta t. And your calculator, if you press that right now when you're in polar mode, automatically it punches a theta for you, right? So again, the bottom line is today we're talking about polar coordinates. And again, polar coordinates are very interesting. You can do things with them that you couldn't do previously. Now, what is the characteristic of a polar coordinate? Okay, a polar coordinate typically looks just like this one. A polar equation looks r of theta equals, basically it's a function of theta. You have things that have a function of theta. For example, this function right here, r equals e to the cosine theta. That is a polar equation. And how does this contrast with parametric? What was the typical parametric equation look like? A typical parametric was x equals to something, y equals to something. Remember that from last class, right? So that's the characteristic of a parametric equation, typically a function of t or any variable. A third variable can be used there. But the way you can recognize a function in polar coordinates is you have r equals, let's say, sine theta. You have r equals a function of theta, then you're talking about a curve that is given in polar coordinates. Okay, so what are we going to do with polar coordinates? What types of things can we do with them? So basically today, and there is no next time, so today we're just going to abbreviate both of these topics. So we're going to talk a little bit about plotting points in polar coordinates, doing some conversions from polar to rectangular coordinates, and again, talking about points in polar coordinates. We already talked a little bit about how to graph things on the calculator, and a little bit more conversions about, how do you convert polar equations this time into rectangular and vice versa. But the most important part we want to get to is really this part, calculus with polar equations, that is finding area within a polar curve. Because everything else, technically you should have seen in trigonometry or pre-calculus, etc. But we're going to do a little bit review because most people from past experience in this class, they don't remember it or maybe they've never seen it. So we're going to assume that you didn't see it or you forgot about it. We're going to review that stuff pretty quickly and then get to the point where we do some calculus with polar coordinates, okay? And also, if there is time left, there is one thing I'd like to show you today, and that is how to evaluate this integral, negative infinity to infinity, e to the negative x squared dx. And you may be very surprised to know the answer. Any guesses what the answer might be? You'll never guess, but give me a guess anyway. Cosine something. The answer turns out to be the square root of pi. Who would have thought? Okay, so somehow, by using polar coordinates, we can actually take a leap into Calc 3, giving you a little bit ideas from Calc 3. I can actually prove that to you today, if we can get that far, and hopefully we will. Okay, so you can do things with polar coordinates you couldn't do before. Like this integral, we cannot do without polar coordinates, but once you have polar coordinates, you're going to be able to integrate it. And to be quite honest with you, what when you learn polar coordinates in trigonometry, it seems almost like an inconvenience. Things almost become more difficult. Graphing seems more difficult. But you will really appreciate polar coordinates when you go to Calc 3. There you'll talk about cylindrical coordinates. So everything is exactly the same, except you also have z equals z. They put a third dimension. And there, integrals that would be very difficult in the past will be very easy once you convert to polar coordinates. So let's see, what it is really. Okay, basically in Cartesian coordinates you have x and y, right? This point right here would have an address x comma y. You give the distance to the x-axis and distance to the y-axis. X comma y uniquely represents a point. In polar coordinates you have the same point, but now we're going to represent it by how far you are away from the origin, which will be r. And what is this theta? This angle typically represent the counterclockwise angle theta. So if you know those two things, you can represent a point, except that it's not unique. Because every time you go in the circle one more time, every time you add 2 pi to theta, you come back to the same point, right? So the problem with, something interesting about polar coordinates is each point is not unique. It could have multiple representations. It actually has infinitely many representations. We're going to see that in just a little bit. So how can we convert from one to the other? Well, first of all, we have these coordinates. Can you look at this triangle and tell me, what is cosine theta in this triangle? What is cosine theta? Cosine is adjacent over hypotenuse, right? Adjacent is x, hypotenuse is r, right? So the ratio is x over r. So if you solve for x, you get x equals r cosine theta. That's one equation. And you can do the same thing with sine theta, right? Write sine theta here. What is sine theta in this triangle? What is sine theta here? Opposite over hypotenuse, which is y over r. So from there you can solve for y, and what do you get for y? Y equals r sine theta. So these two equations will be used to go from polar to rectangular coordinates. And then we also have the opposite equations to go from rectangular to polar. There usually we're going to need it to find an angle. So we write tangent theta in this triangle, which is opposite over adjacent. So tangent theta is y over x. And what can you tell me about r? Something that relates x and y in this triangle. I'm looking for an equation that relates r in terms of x and y. How about the Pythagorean theorem, right? R squared equals, right here, x squared plus y squared. So r equals the square root of x squared plus y squared. So these two sets of equations will be used to convert from polar to rectangular and vice versa. But here's a little note. Make sure you have this note in your notes that I gave you earlier. The note is that make sure you choose theta in the same quadrant as x comma y, because theta typically comes from negative pi over 2 to pi over 2. But we want to end up in the same quadrant, so we have to adjust with that. We'll see examples. Let's begin with very basics. How do you graph a point in polar coordinates? How do we graph a point in polar coordinates? So now you have several points given to you there. But I just want to make a few little changes here. So what you see here is a polar curve or a polar graphing paper. Polar graphing paper. Just because these circles are so tiny, I'd like to change some of the numbers here. Point A, can you change that number 1 to 5? Make this a 5, please. 5 comma 5 pi over 4. And point B, can you change the number 2 to number 4, please? This should be 4 comma 3 pi. And this last one, point E, I want to change that to negative 6. Okay, so we're going to plot these points, and let's just be familiar with what a polar graphing paper looks like. So it just looks like we're back in trigonometry, right? We have kind of like what looks like a unit circle, except you have concentric circles. But each of these lines represent an angle. Like this one is theta equals to 0. The middle one there is theta equals pi over 4. This one is your pi. This is like 30 degrees or pi over 6. This one is 60 degrees or pi over 3. Okay, to plot the first point was 5 comma 5 pi over 4. 5 comma 5 pi over 4. What we're going to do is, again, remember, this is given to you in polar coordinates. This is like r comma theta. So, first of all, locate the theta. In this case, 5 pi over 4. Okay, what is 5 pi over 4, by the way? It's pi plus pi over 4, right? So it's going to be down here somewhere. This is your 5 pi over 4. Basically, it's pi plus pi over 4. So we want to now graph the point 5 comma 5 pi over 4. So how are you going to plot that point? Basically, think of these lines as starting from origin, pointing towards, away from the origin. So when it says 5, first you locate the angle, in this case the line for 5 pi over 4, and move 5 units away from the origin on that line, okay? These concentric circles represent r equals 1, r equals 2, r equals 3 as you go away from the origin. So we want to put our point at point 5 on this line. So go 1, 2, 3, 4, 5 right here. So this point right here represents the point A. 5 comma 5 pi over 4. Okay, can you do the next one, please? The next one was point B, 4 comma 3 pi. This was the point B. 4 comma 3 pi. Where is 3 pi, first of all? Same one as pi, right? Because you're going 2 pi more after that, so same line as pi. So now we want to go in that direction. This is the line from 0 to pi. So go in that direction 4 units. So would everybody agree with this point right here is our point B? Now it gets a little bit interesting when you have negative r values. For instance, take a look at part C. Negative 3 comma pi over 2. This is our point C. Okay, typically you would find the angle first, right? Angle is pi over 2, which is this one right here, pi over 2. And typically you would move along that line, r equals 1, 2, 3. You just move along your concentric circles. But right now we want, what do we want again? We want negative 3. So going in this direction would be your positive r values. But we want to go in the opposite direction because your r is negative 3. Okay, so we're going to go 3 units in the complete opposite direction. So go 1, 2, 3 units. So right here is going to be our point C. Negative 3 comma pi over 2. Can you do the next one, please? D. 3 comma 3 pi over 2. Where does the point D lie? 3 comma 3 pi over 2. It's the same as C, right? 3 pi over 2, you come to this line. This is your 3 pi over 2. If you're going 3 units along that line, that will bring you to the same exact point. So I'm going to call C comma D. They share the same point. So as you can see, there are many ways to represent points in polar coordinates. In this particular case, these two points represent the same exact location. All right, can you graph part E, please? That was negative 6 comma pi over 3. Negative 6 comma pi over 3. So where did you put it? First you go to pi over 3. So first you would go to pi over 3. You would want to go 6 units in that direction of pi over 3. Again, these radial lines start at the origin, go away from the origin. But because of the negative nature, so we're going to go in the opposite direction once again, right? 6 units in the opposite direction. So this line that I do in black is completely opposite of that pi over 3 angle there. So go on that line, 6 units. So we're going to end up right here. So this is your point given in E. And finally, can you finish part F, please? The point was negative 4 comma pi over 6. Negative 4 comma pi over 6. So you go to pi over 6 once again. You're trying to go 4 units in that direction, except you have to reflect it across the other side because of the negative nature. So once again, we're going to go 4 units in the opposite direction. So 1, 2, 3, 4 along this line. So this is going to be our point F. Okay, here's my other question. Can you give me another point that can be used to represent the point F? Instead of using negative 4 comma pi over 6, what else can we use? For example, give me something else for the point F that starts with the point 4. 4 comma what? 4 comma what again? Because basically this angle is pi over 6, right? So this angle should be pi over 6, right? So you want pi over 6 more than pi, right? So what should be there? You already told me that answer. Pi plus pi over 6, which is 7 pi over 6. And what if I did 7 pi over 6 plus 2n pi or 2k pi? Every time I go around the circle, another full circle, it will be the same location, right? So anytime you have a point, you can add multiples of 2 pi. It will give you another point for the same one. So basically, notice how we went from this one to that one. I took the negative of the r. I went from negative 4 to positive 4. And at the same time, what did I do for the angle? I added pi to the angle. So typically that will be the case. Typically, if you want all general representations of a point r comma theta, you can represent them by, so these are going to be equivalent points, negative r comma theta plus pi. And of course, then you can add 2k pi, because every time you go around the circle of one full revolution, you'll get to the same location. And same thing here, you can add 2k pi to this. That will be also equivalent. So when they ask me for all representations, typically it's going to be this one and this one. Okay, let's go to the next example in our notes. We're going to convert some points now first from polar to rectangular. Let's do part B. Let's just do part B here. So convert the given points from polar form into rectangular form. So we know that x is equal to, what is the formula for x from the first page? R cosine theta, and y is equal to r sine theta. Our r is, because these points, as they are given, are in terms of polar, so r comma theta is what's given to us. So what is the x coordinate going to be? Negative 1 times cosine of pi over 4, right? And the other one will be, again, r is negative 1, theta is pi over 4. This time I want the sine, of course. And what do we get? Pi over 4, cosine and sine are both root 2 over 2, right? So we get negative root 2 over 2 and negative root 2 over 2. Now, which quadrant does that point lie? Both coordinates are negative. Which quadrant would that be? That's the third quadrant, right? X is negative, y is negative. And where does this point lie? Negative 1 comma pi over 4. Well, technically we're going pi over 4, right? But because it's negative, you're going to go in the opposite direction 1 unit, right? So that also lies on the third quadrant. So it makes sense, right? The polar coordinate lies on the third quadrant, and the rectangular coordinate lies on the third quadrant. So the rectangular is really negative root 2 over 2, comma negative root 2 over 2. So this, you know what this point is, what that point is. You also know what this distance is. So we went from polar to rectangular. Okay. Now I'm going to ask you to do the reverse. And let's do part B on the next example also, please. Part B on the next example. How can we go from, this time from rectangular into polar? So to go from rectangular to polar, you're going to use the other two equations that we had on the first page. What were those equations? R equals the square root of x squared plus y squared. In other words, r squared equals x squared plus y squared. And then tangent theta equals y over x. The only thing to be careful is you need to choose theta in the same quadrant as the point. That's the only thing to be careful about. Okay, so let's start then. When you end up, they want to go from rectangular to polar. Your final answer should look like this. R comma theta, correct? distance from the origin, comma, the angle. All right, so let's find r first. That'll be easier. R equals the square root of what? And because this is given is rectangle, this is your x comma y, right? So the first one squared, which is 3. The second one squared, which is 1. So we're looking at the square root of 4. In other words, r is equal to 2. So we got the first coordinate for the polar equation, for the polar point. Is there wrong with me on this one? Because again, some of you have never seen it before. Some of you may have some familiarity. So please stop me if I'm going too fast on any example. All right, everybody agrees on r equals to 2? Okay, how about the angle theta? The angle theta. So we're going to use tangent theta to get the theta. So tangent theta equals what for this example? Y over x. In this case, it's going to be negative 1 over the square root of 3. Okay, at the moment, let's forget about the negative. If tangent theta is 1 over radical 3, what angle would that be? That's when the sine is 1 over 2 and the cosine is root 3 over 2. Which angle was that? Where sine is 1 over 2, cosine is root 3 over 2. And the ratio is 1 over radical 3. Pi over 6. Pi over 6. At pi over 6, tangent theta is 1 over radical 3. So it's going to be at negative pi over 6 that is equal to negative 1 over root 3. But now we have to pick the right quadrant, okay? Where is the original given point? In which quadrant? Negative root 3 comma 1. X is negative, but y is positive. Where is that? That's quadrant 2, right? Okay, so what I need is I need an angle that will represent that point in that quadrant, but that angle should have a reference angle of pi over 6. So this angle here will be pi over 6. So what angle should you end up with here? Pi minus pi over 6, which will be 5 pi over 6. So your angle should be pi minus pi over 6, which is 5 pi over 6. So we can leave the answer as 2 comma 5 pi over 6. What if I wanted to leave the answer as a negative angle? Say it's going to be 2 comma a negative angle. What else could I have written here? If I want a negative angle, then I would go this way around, right? And what angle is that? So you're going negative, so negative pi plus pi over 6, right, in parentheses. So what is pi plus pi over 6? 7 pi over 6. So you can also leave it as negative 7 pi over 6 if you went around this way. But again, if that's confusing you, don't worry about it. There's so many ways to write these that sometimes I get carried away trying to write them in so many different ways. But a typical question might ask you, it might say, okay, give me all possible representations of this point. How would we do that? All possible representation. Insert the other question for me. Yes, exactly. And you want to end up in the correct coordinates. So the theta you get from solving tangent theta equals y over 6 is your reference angle for these problems. Only the reference angle, exactly. Okay, so I want all possible representations of this point. So one way to write it, it would be 2 comma 5 pi over 6 plus 2k pi. So you go around the circle. Every time you go around, you come to the same point. And I also want to represent as a negative r. So let's say negative 2 comma. So basically now I want you to tell me this angle. And that's 11 pi over 6. So the 11 pi over 6 or negative pi over 6 plus 2k pi. Basically, when you want all possible representations, if you're going from r to negative r, all you have to do is really you're adding pi to the original angle, and that will represent those reflections that we're looking at. Okay, I think you guys can do part A. That's not going to be as complicated as part B. So again, these are quick review questions of polar before we can get to the point where we can do some calculus with polar equations. Okay. Okay, I'm going to give you guys the answer for part in case you did it later and you want to check your answer. One possible representation is root 2 comma negative pi over 4 plus 2k pi. And another representation would be negative root 2 comma 3 pi over 4 plus 2k pi. Again, there are other forms possible, but if you understand it, then you'll know which ones are equivalent. So now let's go to something a little bit different. This time we're going to try to look at some quick graphs in polar coordinates. So here's the beauty of polar coordinates, and someone earlier said this. I was asking, when is it a good time to use polar coordinates? Typically, when you're dealing with circular regions, polar coordinates make things a lot easier. So, for example, r equals to 2. Guess what kind of a graph that represents in polar coordinates? No matter where you are, distance from the origin is equal to 2. That's a circle centered at 0, 0 with radius of 2 units. So, isn't that much easier than rectangular coordinates where you have x squared plus y squared equals to 4? Much more complicated looking equation, right? So when you deal with circular regions, it becomes so much easier to work with polar coordinates. Things, when you do integration over circular regions, double, triple integration in Calc 3, just convert things into polar and it's going to be easier. What about this one? R is between 0 and 2. That's basically the whole circle and also everything inside filled in. That entire region is being represented by r is between 0 and 2. What about theta pi over 4, r greater than 1? First, let's graph that radial line, theta equals pi over 4. And technically, I could also do it this way, because r equals pi over 4, rather theta equals pi over 4. If you have negative r values, you would be on the other side of that line, right? But which part do we want right now? We want everything greater than 1. So this represents the concentric circle 1. So we want everything greater than 1. That would be that line right there. What about r equals secant theta? Let's rewrite that. Secant is 1 over cosine theta. So go ahead and try to write it in a more familiar format. What would you suggest? In r equals 1 over cosine theta. Any thoughts what we could do to this one? Good. Rewrite it. R cosine theta equals 1. And what do we know about r cosine theta? This is one of the formulas we looked at today on the first page. R cosine theta is the same thing as x. So this is like we're saying x equals 1. What kind of a graph is x equals 1? X equals 1 is a straight line, a vertical line, right? X equals 1. Except that this line is going to have a lot of little dots that are holes, because the original one is not defined at which values. Anytime cosine theta is 0, this is not defined, right? And when is cosine theta 0? When theta equals when? Cosine theta is 0 when theta equals pi over 2. Where else? 3 pi over 2. So every time you go around, add another pi or subtract another pi, cosine theta will be 0. So it has infinite discontinuities. Every time theta reaches that value pi over 2, so there's going to be a lot of little dots, open circles along that line. But roughly speaking, the points are going to be along x equals 1. What about something like this? R equals theta, theta greater than or equal to 0. What kind of a graph would that be? R equals theta. So as theta is getting larger, I want to go back to my polar graphing paper so I can show you this better. Okay, let me get another color here. So you start at theta equals 0, and you're going to go around the circle that way. And as you're getting around the circle, your r is getting larger. So maybe first you were here, then you get a little bit away from, so then you're here, then you keep getting farther and farther away from this center as you go around. What kind of a graph do you think we're getting here? It looks like it's going to be a spiral, exactly. It looks like it's going to be a spiral. And you can actually graph this one on the graphing calculator. There's an interesting lesson to be learned here. Let's go to y equals. And I'm just going to turn the first one off by pressing enter on it. It turns it off in case I need it later on. Okay, just enter theta. Remember, theta is just, you press the x key here. We're in polar coordinates, if I remind everyone. R equals theta. And for the window, I want to make x maximum. I want to make x maximum and y maximum, both of them larger. Let's make them from negative 20 to 20. Also for the y, negative 20 to 20. And let's take a look at the graph. Just like we expected, a beautiful spiral. Again, try doing that in rectangular coordinates. Now let me ask you a trick question here. If I go back to my window and I change theta step, right now it's 0.1. Okay, so it's every 0.1 unit is plotting a point basically. That's 0.1 radians. Say I'm going to make it pi over 2. I don't normally recommend this. Normally 0.1 is a good theta step, okay? But if I make it pi over 2 and later come back and change this, okay? Don't forget it at pi over 2 because it's going to give you weird graphs. Now I'm going to show you what the graph looks like. What happened there? Can you tell me what's happening there? Why is it not doing the spiral, but it's doing this diamond shape? It's only graphing at increments of pi over 2. So it's graphing this point right here, then it's going here, it's graphing that point, and then it's trying to join down with straight lines. So it's ending up with this figure. Whereas if you let theta step to be 0.1, it's trying to plot a point here, a point there, a point there. It's trying to plot a lot of points. It's smoothing it out basically. And this is not really the accurate graph. Okay, this makes a nice, interesting visualization. But the accurate graph is when you have theta step being small, something like 0.1. And I'm going to leave it at 0.1. I don't want to confuse the next math teacher who comes into this room to see what's happening there. Okay. All right, so let's go back to the next page. Aha. Graphing a polar equation. So far we did the easy ones, like r equals to 2, theta equals pi over 4, things like that. Now this one I'm just going to give you some very brief understanding how you can do this. But these are really neat because the long way would be to graph r equals sine theta, for instance. You would do point plotting. Okay, you get a polar paper. You know, you have theta, you have r equals sine theta. So you plot lots of different values like 0, pi over 2, and so forth. And you plot them. It's quite tedious, but there is actually an easier way. Okay, are you ready for this easier way? Now, do you recognize this graph as sine x? Because you need to have that to begin with in this new method that I'm going to show you. So we're trying to graph this polar graph of r equals sine theta. Okay, please don't take a sneak preview yet. Please don't use your calculator yet. Let's try to figure it out, and then you can go back and check on your calculator, okay? And the way it's going to work is concentrate on these lines, okay? What is the distance here? What is the distance here? What is the distance here? And so forth. What is happening to these distances? They're getting bigger and bigger. These distances is what we're going to represent by r. So, but except that now it's going to be r will be how far you are away from the origin. So going from 0 to pi, r went from where to where? It went from 0. First, let's do up to pi over 2. That's going to be easier. Let's do up to pi over 2. So going from 0 to pi over 2, r went from 0 to 1. Now remember, this is theta equals 0. This is theta equals pi over 2. So going from there to there slowly, they should be increasing. So, and you want to end up at 1. This is the point 1. Technically, you would be plotting these points one at a time. Okay, and then from pi over 2 to pi, what's going to happen to these distances? Over here, from pi over 2 to pi. Over here, what's going to happen? They should decrease. It should go from 1 to 0. So 1 back to 0. Again, this is the point where r equals 0, right? What if you go around it one more time, from pi to 2 pi? What is going to happen? For example, from pi to 3 pi over 2, what will happen? It's going to go from 0 to negative 1. But remember, what does negative r represent? You have to reflect in the complete opposite quadrant, right? So it's actually going to end up over here again. Okay? And what about from here to here? From 3 pi over to 2 pi, it needs to go from negative 1 to 0. So in this quadrant, it wants to go from negative 1 to 0. But again, reflected to the opposite quadrant, there it's going to be from 1 to 0. So what happens is basically this circle is traced twice as you go from 0 to 2 pi. So if you just graph on your calculators, if you just graph 0 to pi, just go to y equals, graph r equals sine theta. But just make the window from 0 to pi. That's really all you need. Theta max, I'm just going to go to pi. If you like, keep it 2 pi to see if anything else is going to happen there. And this I'm going to go from, let's say, negative 2 to 2 on both sides. And it's not looking exactly like a circle, but you can play with it. You can go to window or zoom square. That makes things more look like what they should be looking like. Because so that's the circle that we got. That's the circle the calculator is given. The nice thing that we determine is that this completes one full revolution from 0 to pi. Can you do the next one? Let's do this one. From theta equals 0 to theta equals pi over 2, what is happening to the r values? From theta equals 0 to pi over 2, r values are going from 1 to 0, correct? So we're going to go from, so if we started here, by the time you're done here, you should be going from 1 back to 0. And what about from pi over 2 to pi in this quadrant? From pi over 2 to pi, what should be happening here? They are going from 0 to negative 1, except negative means you have to reflect in the complete opposite quadrant. So now you should be over here, and you should be going from 0 to 1, basically. So how will you finish it? So you want to go from 0 to back to 1. And if you continue on, you're going to see that it will retrace the circle one more time. So you see r equals cosine theta. It turns out to be a circle that wraps around the x-axis. R equals sine theta. It turns out to be a circle that wraps around the y-axis. And the really nice one I would like for you to try is this one. To graph r equals cosine of 2 theta. I think it's on the next page, or maybe at the bottom of your page. Okay, r equals cosine of 2 theta. Let's go in segments of pi over 4. So first tell me what's going to happen from 0 to pi over 4. What's going to happen to r? And this is 0 to pi over 4 over here, right? This is your pi over 4. So what should be happening? We should start where? At 1. And where should you end up with? By the time you end up from 0 to pi over 4, where should you end up in terms of r? At 0. So we're going to start here, and at the end of pi over 4, we're going to end up at 0. 0 meaning r equals 0. We're back at the pole, as they call it, the origin. Okay, what is going to happen from pi over 4 to pi over 2? So that's this quadrant over here, right? It should be going from 0 to negative 1. But remember, negative means go in the complete opposite quadrant, which is over here. So we're going to come over here. And we're going to go from 0 to 1. So basically, this is still 1 units. because we're talking about, when you talk about polar coordinates, you have these concentric circles. So, I label this with Cartesian coordinates, but technically with polar coordinates, your r equals to 1 is this, right? Everywhere here you have your r equals 1. Then you have r equals to 2 is this, r equals to 3 is that, and so forth, right? Okay, tell me what will happen from pi over 2 to 3 pi over 4 in this region right here. What do you expect to see? You want to go from r equals -1 to r equals 0, so except reflected a complete opposite quadrant. And now you want to go from r equals 1 to 0. So now you can continue this on. I think it turns out to be something like this. If you finish it up, and let's check this on the calculator. Basically, you can finish the whole thing without lifting your finger out. It's just a continuous motion. And let's go to the calculator and graph a cosine of 2 theta. Now try doing that by point plotting. It becomes practically impossible. So it's really easier, this approach, although at first it may look a little bit confusing. Okay, why did it stop there? On my calculator, it stopped. Because I was only going to pi. This one needs 2 pi to complete one full revolution. So I should go back to the window and put 2 pi. And to see a better graph, technically I would go back to window and x min and x max. I may want to make it like negative 1.5 to 1.5 in each direction. In a little bit, we're going to talk about how to find the area within that curve, talking about calculus with polar curves. So first, we're trying to get some more familiarity with them. And again, this is called the 4-petal rose. They have these weird names. You don't have to memorize them, obviously, but we're going to learn about how to find the area within one petal in just a little bit. Okay, any questions before we look at the next problem? Again, we're still in trigonometry phase. We're still reviewing a little bit basics of polar coordinates, but we're not too far away from where I can introduce to you the calculus. And really, because of the limited time we have, we're only going to look at area. But if you look at your textbook, they do things like arc length in polar curves, tangent lines in polar curves, and you can do all sorts of different calculus things with polar coordinates. We're just going to do area today. Okay, this one also looks like, okay, conversions, but you might say, haven't we done conversions already? Isn't that enough? Well, we've done conversions, but they were points. Now we're converting an entire equation from polar to Cartesian. And there are a few little tricks that I'd like to show you here. Look, r equals 4 sine theta. How can we go back and write everything? When you end up with this, you want to end up with just x's and y's, nothing else. That's what it means to be in Cartesian coordinates, just x's and y's. What could I write for r, for instance, in terms of x and y? Any thoughts? What could I write for r? The square root of x squared plus y squared, right? That was one of the formulas we had earlier. What could I write instead of sine theta? We had earlier y equals r sine theta. So sine theta is y over r, except I don't want to write r. Instead of r, what could I write? R is once again the square root of x squared plus y squared. Again, so r is, so first we needed sine theta. Sine theta was the same as y over r. So I tried to put it back here, but for the bottom I didn't want to keep the r. Remember, we're trying to convert things into Cartesian coordinates. Then we have this. And you could leave it like this, but typically you would multiply both sides by the denominator, and you're going to end up with, you lose the radical, right? And what kind of a graph is this? It's a circle. How do you know it's a circle? You see the x squared plus y squared, right? But what you can do is you can put the 4y on the left-hand side. You remember a method called completing to a perfect square? You could do that. You could basically, this part is optional, but if you just remove that to the left-hand side, and if you could somehow complete that to a perfect square, so you're going to have to add a number to both sides, what number would that be? Square of the half of the middle term, right? So half is 2, square root 4. If I add 4 here, I should add a 4 here, right? So look what happened here. So what kind of a circle is this? The center is at 0, 2, and the radius is 2 square, or the radius is 2 units. So basically it's going to be a circle like this. And based on what we graphed a little while ago, r equals sine theta was a circle that wraps around the y-axis, remember? R equals cosine theta was a circle that wraps around the x-axis. And this one happens to have a radius of 2 units. It goes to the highest point on the y-axis is 4. Okay, this one looks really weird. The next example. Can we convert that into x's and y's, aka Cartesian coordinates? Can we convert that one? What do we know about r sine theta? That's y. Okay, the right-hand side, can you combine them somehow? As a single logarithm, what is this? R, exactly, you multiply the quantities within the logs. And what is r cosine theta? X, right? So here we have y equals ln x. So very, very interesting, because some things are easier in polar coordinates, but some things are a lot harder. Think about y equals ln x. What is it going to look like in polar coordinates? R sine theta equals ln r plus ln cosine theta. So a lot more complicated, right? But something like a circle, especially this circle right here, it was pretty complicated in polar. Rather, it was pretty complicated here in rectangular, but it was so easy in polar. So, you know, certain things, especially circular things, are easier in polar coordinates. Okay, I'm going to let you guys convert this one into polar. It's not going to be any tricks involved. Just for x, write r sine theta. I'm sorry, for x, you write r cosine theta. And for y, you write r sine theta. And you just square them, so it's going to be no tricks involved. If you can simplify it a little bit, fine. If not, don't worry about it. So that's... so you can go backwards, obviously. You can go from rectangular to polar. And finally, though, we're at a point where I want to show you this formula I've been talking about. We're going to find the area within polar curves. We're going to do calculus within polar equations. This is the new stuff, technically, unique to this class. So let's take a look. First of all, in your handout, you have the formula. Okay, so you don't have to memorize this formula. You know, if you had seen this on any in-class quiz or something, I would have given the formula to you anyway. But know how to use it, and know a little bit about how is it derived. So basically, say this is your polar curve right here. This is your polar curve from the point theta equals alpha to the point theta equals beta. And let's say you wanted to find the entire area of that region from theta equals alpha to theta equals beta, this entire region. Okay? And the answer is 1/2 of the integral, whatever the equation of that curve is in polar coordinates, you square that. So basically it's 1/2 r squared d theta. That's what the integral of that quantity is going to give you the total area. Now, how do they come up with that formula? I'd like to quickly point that out to you. So we begin with a thin sector. We begin with a thin sector, and we call that angle delta theta, an incremental angle in theta. Okay? So from here to here is your r of theta. That's r. This angle is delta theta. Now we're going to assume this is a thin slice of a circle, because if they're thin enough, they're going to look like a sector of a circle. How do you find the area of the sector of a circle? First of all, what is the area of an entire circle? Area of an entire circle with radius r. area of the circle is pi r squared, right? Pi r squared. So instead of r, we have a variable r. We have r of theta, so pi r squared. But we're not taking the entire circle. What portion of it are we taking? This little delta theta divided by 2 pi. Okay, so you're not taking the entire circle. So you should multiply this by the fraction of the circle you're taking. In this case, this angle is just a small angle, delta theta. So you're only taking the fraction of delta theta over 2 pi fraction. So multiply everything by delta theta over 2 pi. The pi's cancel, and you are left with this quantity. So 1/2 r squared, that's what the 1/2 is coming from. And the delta theta, as you have many of these sectors, you're adding them up, it becomes d theta. Again, we're integrating it because we're going to sum up the areas of all such sectors. So again, area equals 1/2 times the integral of whatever the equation is given to you, you square that d theta from the given alpha to the given beta. The important thing, though, is there should be no discontinuities. This should be a smooth curve. And also, the curve should go around this only once. So, for example, that circle that we saw earlier, if you go from 0 to pi, this is going to be, it's going to go over this one time, okay, 0 to pi. If you go from 0 to 2 pi, it's going to go around this again. So if you were trying to find the area enclosed by that curve, you need to go 0 to pi only. So it should only be traversed one time during that integration process. Let's do our first example. I'd like to do the other one first, the one with the sine function. You'll see why in a minute. Find the area enclosed within one petal of r equals 2 sine of 3 theta. Okay, anytime we're talking about area, it is a good idea to look at the graph first. So if you like, go ahead and graph this function. Let's see what kind of a graph we're getting on the calculator. Sine of 3 theta. Again, make sure you're in radian mode. Make sure you are in polar mode. Again, all of that is done to the mode key, of course. So we go to y equals, and I'm going to enter 2 sine of 3 theta. Okay, currently I'm going from 0 to 2 pi. But I don't like to, because 1.5 is going to cut it off a little bit, so let me just at least go from negative 2.5 to 2.5. You want to include the 2 in your range, basically. Okay, so this one happens to have 3 petals. And sometimes I'm curious. I'm going to try 0 to pi just to see if it actually finishes the entire graph there. It did. You see, so there's really no telling from where to where, or at the first glance, there's no telling that it's going to finish the curve from 0 to pi or 0 to 2 pi and so forth. So the method I'm going to show you right now, it doesn't matter. It doesn't matter if it finishes from 0 to pi or 0 to 2 pi. This method is still going to work. So again, roughly speaking, this is the graph that we had. Okay, here's how we're going to solve these questions. To find the area within one petal. Notice when r equals to 0, it starts at 0, right? I will find out from what angle to what angle does it come back to 0. Okay, so if I can find that out, I'm going to find then the 2 theta ranges that I need to find the area within one petal. And here is how I'm going to solve an equation. So I need to know when is 2 sine of 3 theta equal to 0. When is it equal to 0? First, divide both sides by 2. So when is sine of an angle equal to 0? If that angle is equal to what? When is the sine function equal to 0? It's 0 at 0, right? Where else is 0? Sine function? Pi over 2 it's 1, right? Sine is 1 there. Where else is it 0? So sine function is 0 at 0. Where else is 0? At pi, at 2 pi, every time you go around another pi. So basically it's 0 at 0, at pi, at 2 pi, and so forth. I don't really have to list all of them. But then what does it tell you about theta then? Divide both sides by 3. What do you get? 0 over 3 is 0, pi over 3, 2 pi over 3, and so forth. So what we're saying is the first time it's going to hit 0, it's going to start at 0. By the time it goes an angle of 2 pi, an angle of pi over 3, if I was to be able to graph this on polar paper, you would see that that pedal has been completed from 0 to pi over 3. Okay. So when I integrate this, guess from where to where I'm going to integrate this. Exactly, I'm going to integrate this from, say it again, 0 to pi over 3. And the formula says 1/2 r squared, r being 2 sine of 3 theta quantity squared. Could I have integrated this from pi over 3 to 2 pi over 3? Yes, I can also do that. That will be the other pedal, and because of symmetry, they all have the same area. But which one do you think will be easier? 0 to pi over 3 or pi over 3 to 2 pi over 3? The first one, if you have a 0, it's going to be easy to plug the limits in, right? So let me give everyone a little bit of time to try to work on this integral. And I must say that the hardest thing in finding these area within a polar curve, is determining the limits of integration. Because if you can determine the limits of integration, the integral usually becomes pretty straightforward. So please make a note of this formula as a reminder, the reduction formula for sine squared, because we're going to need that as we solve this example. So we're going to use those formulas to simplify this first of all, right? Okay, then I'm going to put the equivalent version for sine squared, factoring out my constants first of all. Sine squared is 1 minus cosine of the double angle, all over 2. And this 2 in the denominator can be taken outside, so now I have 4 over 4 or just 1. And how will I integrate 1 minus cosine 6 theta? Integral of 1 is theta, right? Integral of cosine is sine, except sine 6 theta divided by 6. Because of the k theta, you divide by k, right? It is integrate. And now we want to work on the limits. 0 to pi over 3. Again, this 2 I've already factored outside in my next step, so I didn't have to have it in my step here. So we have theta, which is pi over 3, minus sine of 6 times pi over 3. What do you get there? Sine of 6 times pi over 3? That's really 2 pi. And sine of 2 pi is 0. And if you plug in a 0, you also get 0. So it looks like all we're getting here is pi over 3. So that's the area within one pedal. And sometimes they ask the question, what is the total area traced by this curve? If that was the case, you would multiply by 3. If it's just area within one pedal, then it would be pi over 3. Okay. And what about the other example? It looks similar, but yet it has a little twist to it. Let's also take a look at that one before you try the ones on the group activity, which will give you enough practice before you try the one on your assignment. r equals cosine of 2 theta. Again, it would be helpful to start by graphing this to see what we're looking at here. Cosine of 2 theta. Again, I was graphing it from 0 to pi earlier, so to finish it, I'm going to now graph it, make sure I did from 0 to 2 pi. I want to see the full. Okay, so this is your standard 4-petal rose for cosine of 2 theta. Yes, question.
They're not symmetrical.
Actually, they should be symmetrical. It doesn't look like it's symmetrical because of the screen is more rectangular. If you do zoom square, it's actually going to show you that all the petals are of the same size. It's a good question because sometimes we make that assumption. We find area within one petal, assuming that all petals will have the same area. Okay, so where did this one start? When theta is 0, what is r? It started at 1, right? When theta is equal to 0, it started at 1. Then my question is, when is the next time it hits the pole, the 0, 0 point? So set equal to 0, set r equal to 0. When is cosine function equal to 0? When the angle is equal to pi over 2 or 3 pi over 2. So solve for theta when theta equals pi over 4 or 3 pi over 4 and so forth. So now it is possible to solve this problem to go from pi over 4 to 3 pi over 4. You know what we're going to find if we do that? Because at pi over 4 basically it comes to this point. Pi over 4 to 3 pi over 4, chances are we're going to get this rotation, this petal. But there is another way. What else could we do here? If you go from 0 to pi over 4, what are you going to find from 0 to pi over 4? Zero to pi over 4, it does this drawing. If you found the area from 0 to pi over 4, what would you have found? Area within half a petal, okay? And then you can double it to find the area in the entire petal. So you either go from pi over 4 to 3 pi over 4, which will give you this one, or you can go, so I'm going to say area of half petal equals, the formula says, the formula already had a 1/2 in it, right? 1/2 r squared theta d theta. In this case, r squared is cosine square of 2 theta d theta. And the angle should be, if I'm only finding half a petal, what should I use? 0 to pi over 4. Again, just know that you could have gone from pi over 4 to 3 pi over 4. You can do that. But in my case, first I found area of half a petal, then area of full petal, 1 full petal, equals 2 times that as much. 2 times a half times the above, basically. And how can I rewrite cosine square of 2 theta? One plus cosine 4 theta over 2. And how do we know that? Because again, we're reminded of the reduction formula. Cosine square is 1 plus cosine of the double angle over 2. And once again, I'm going to take out the 1/2. So then I only have to integrate 1 plus cosine of 4 theta. Okay, integral of 1 is theta. What about integral of cosine 4 theta? Sine of 4 theta divided by 4. We're going from 0 to pi over 4. And what do we get? Once again, when you plug in pi over 4 in the sine function, excuse me, this was theta here. Right. When you plug in pi over 4 for theta, you get sine of pi, which is equal to, if you plug in pi over 4 in, because I factored this 2 outside in the next step, that's where the 1/2 came from. Was that the 2 you were asking about? Okay, the 1 prior we canceled because we first set up the integral for half a pedal. For the full pedal, I had to double it. And then we had another half coming from the formula, from this other formula. So my question was now, this pi over 4 plugged into here for sine of 4 theta, what will you get? Exactly, because 4 times pi over 4, the 4's cancel, sine pi is 0. And then again, plug in 0 for theta, you get nothing. The final answer, pi over 8. Okay, any questions about that one? So they can each be slightly different, but if you know how polar graphs work, if you can graph them before you find the area, and sometimes you do half a pedal, sometimes you do a full pedal, sometimes you do the entire region, like there are some graphs that look something like this, that you can do the entire 0 to 2 pi in one shot, if there are no pedals to deal with at all. So, this gives you the general idea, but pretty much you'll be able to do the questions that I have assigned based on these 2 examples we've done on the polar curves. So this is going to be your preview to Calc 3 now, the preview to Calc 3. I'm going to try to explain to you how do we integrate that question I asked you earlier from negative infinity to infinity. How do you show that this is equal to the square root of pi? Looks really weird, right? Well, before I can get there, I need to give you a little preview of Calc 3, a double integration preview. Okay, this is how it's going to work. Okay, let's say that you had a situation like this: x dx dy, and let's say that x goes from let's make it 2x. X goes from 0 to 3. Y goes from 0 to 2. Let's say. So the way you read this is you go from the inside to outside. If the dx comes first, that means you're going to first look at this integral with respect to x. Once you do that, you're going to do the other integral with respect to y. Okay, that's the way it works. Now, what is the integral of 2x with respect to x? That's x squared, 2x squared over 2, or x squared. And integrate from 0 to 3. So the outside is still there. The outside integral is still there, 0 to 2. The dy is still there, right? So what is the integral of this? So x squared 0 to 3, you get 9, right? Okay, 9. So now integrate 0 to 2 of 9 dy, which is 9y going from 0 to 2, and we get the final answer of 18. Now, I have to say this was an easy question as far as double integrals go, because sometimes you have things, like here I have just variable x, right? Sometimes you might have x squared y plus xy squared. Your limits could have x's and y's, but the idea is simple. You start from inner, you work yourself towards outside. That's how you do double integration, okay? Now, to do this integral, which, by the way, comes up a lot when you're doing area under the bell-shaped curve, okay? That's where this one comes up a lot. A genius mathematician figured out the following. Let's call this I, the integral. Instead of finding I, we're going to find I squared first. The same integral multiplied by itself. So here's the integral, negative infinity to infinity, e to the negative x squared. If you multiply the same integral by itself, but this time they use the y variable. Technically, it's the same thing, right? Whether you use the x variable or the y variable. I could use t, whatever, same. But, okay, here I want you to take a little leap with me, because I'm going to show you something that you haven't yet seen, which is, if you have a situation like this, you can put the 2 integrals together. Okay, negative infinity to infinity, negative infinity to infinity, and put the other two functions together. And now you have dx dy. Okay. How can you simplify this for me? How can you simplify that? E to the power of negative x squared plus y squared. Could you live with that? You see reminiscence of a circle. The x squared plus y squared reminds us of a circle. Now here's the thing. Here's what you're going to learn early on in calculus. You're going to learn this. If you want to, so instead of x squared and y squared, by the way, we don't know how to integrate this, right? This is impossible to integrate. So we're going to shift our universe now. We're going to go from Cartesian to polar. So instead of x squared plus y squared, what would I enter there? E to the negative r squared, right? And here, this is one thing you're going to have to learn, so if you can't swallow that right now, instead of dx dy, you're going to learn, you're going to replace it by this, r dr d theta. And if you give me a minute after class, I can explain to you, but right now let's assume that, okay? Instead of dx dy, you're going to, anytime you switch to polar, you're going to have r dr d theta. But you also have to switch your limits of integration. These are going from negative infinity to infinity. Okay, limits for r. If you're going from negative infinity to infinity, what should r be? From 0 to, r starts at 0, right? It should be from 0 to infinity. And what about theta? What should theta be? You want to cover the entire plane with theta, so you should go from 0 to 2 pi. Okay, so theta will go from 0 to 2 pi, and r will go from 0 to infinity. So theta goes from 0 to 2 pi. This way you cover the entire plane. Every single point on that has been covered, just like before, negative infinity to infinity. Now, can you integrate e to the negative r squared times r? Can you integrate that? How do you integrate this? Use substitution, right? Let u be negative r squared. Du is negative 2r dr. So r dr is what? R dr is du over negative 2. Now this is calculus 2. This integrating e to the negative r squared times r. That should not be a huge, shock to us, right? We should be able to do that part. So this inner part then, what will be the integral of this whole thing then? What will this integral be? Negative 1/2 integral e to the u du. What is that? Negative 1/2 e to the u being negative r squared, right? You put the u back in there. So this whole thing becomes negative 1/2 e to the negative r squared from 0 to infinity. You still have the outside sitting there, d theta. What do you get when you plug in infinity? What will you get? Because e to the negative r squared can be written like this, right? Right, when you plug in infinity, 1 over infinity is 0, you get 0, minus, plug in 0, and what do you get? What is e to the 0? 1, but you have a negative 1/2, so it'll be plus 1/2. We're almost there, okay? So now you have plus 1/2. What is the integral of 1/2 with respect to theta? 1/2 theta. Going from 0 to 2 pi, what do you get? The 2's cancel, you get pi. But remember, what was this everything equal to? I squared. So guess what? I equals the square root of pi. That's the integral that we're looking for, right? So this is like one of the masterpieces of all of calculus. But I gave you a little preview to it. If it went a little bit over your head, don't worry about it. You'll probably see it again sometime in the future.